Hello and welcome back to week 6 of remote learning. In this video, I'm going to be talking to you briefly about the ideal gas law. Now, if you haven't already watched the other video I shared with you on the steel drum implosion, go back and watch that now. I'm going to be talking about what's going on in this video and how this relates to the ideal gas law. So if you have watched the video about the steel drum implosion, great. We're going to use that information to talk about the ideal gas law. Now in the video, we saw that there was a steel drum that was being heated up by a fire or some sort of heat source. And as the steel drum was being heated up, the particles inside the drum started spreading out and moving faster and faster. They were hitting the sides of the container more frequently. This means that the temperature inside of the steel drum was very high. Those particles had a lot of energy to be moving about very frequently. The pressure also inside this steel drum is because the temp was so high, the pressure was high. Those particles were expanding and putting pressure against the sides of the container. The volume of the steel drum was a fixed set volume. Since it was steel, it couldn't expand at all as the pressure was increasing, but it was still a large volume. Now the number of particles was fixed. There was a set number of particles inside the steel drum. They closed the lid so that no particles could come in or escape. Now as soon as they took that steel drum and they started cooling it down, they moved it to a bucket of ice. When that steel drum was on the ice, the particles inside started to do something interesting, which changed a lot of these variables. The particles started to cool down, so the temperature went from high to low. Now when the temp goes down, those particles lose energy and they start condensing. When they start condensing, the pressure also goes down. There's not pressure anymore going against the sides of the drum inside. Those particles are condensing. And so the pressure outside the container actually becomes greater than the pressure inside. And since this is a fixed volume where particles can't go out or inside, the volume had to become smaller and less, and so the pressure outside the drum crushed this can and we saw it implode. This example is a great demonstration of the ideal gas law. And in the ideal gas law, we see how these 4 different variables interact with one another in a unique way. Now the formula for the ideal gas law is PV equals N times R times T, where P represents pressure. Now the pressure stands for how often those particles inside a container are hitting the sides of the wall. So a high pressure has a high amount of particles hitting the wall, where low pressure, those particles are hitting the wall less frequently. The unit we use to describe pressure is ATM, which stands for atmospheric pressure. V represents volume in this ideal gas law formula. Volume is essentially how big or small the container is that contains the gas particles. We use the unit of liters to describe volume. N in this formula represents the number of moles. Moles is the number of particles of gas that we are working with. And like you might guess, the unit for moles is MOL, or mole. The R in the formula stands for an ideal gas constant. Now a constant is a number that stays the same. Unlike the other variables that can change, they can vary, this is a constant number that is 0.0821, and the units are liters times ATM divided by moles times K. The final unit here in the formula is T, which stands for temperature, and that essentially is how fast the particles are moving. So yeah, we're used to talking about temperature in terms of how hot or cold something is, but in this case, we want to use temperature to describe energy or how fast or slow something is moving. The unit we use to describe temperature is this unit Kelvin, which is different than Fahrenheit or Celsius that we might be used to. It's a scientific way to describe temperature that has absolute zero being at zero. But this is the ideal gas law formula. In the next tutorial videos, you're going to be learning about how to use this formula to solve problems involving ideal gases. Until next time, see you later.